Hello students, very good evening. So today we'll be discussing about a very small topic which is very important topic also, which is capacitor. So what is capacitor? Probably all of you would have heard about it, like in our houses every day that we use, right? There is something which probably they call it as a condenser. Right? So this condenser, probably whenever a fan is not rotating well, right, the first thing that you change is this capacitor or this condenser we call it. So what is this condenser? Like there are many places where we use it. Let's say for example, life-saving purposes, defibrillator, like the one which probably save human from their heart attacks. Or they have any blockage by giving some sudden electric impulse, it will try to make it save lives of people by defibrillator. So that is basically very important for the students who are studying NEET or JEE. The NEET level probably all there are very medical advantages for capacitor, like probably a very high clarity ultrasound or X-rays. Definitely need this capacitor, right? And also engineering students, right? They have to there are many places where we use this capacitor, like fans, any electronic devices you take, capacitor is definitely going to be there. Many electrical and electronic devices, capacitor is going to be there. Robots or AIs, whatever, name it. Definitely, knowing capacitor is very important. Right, ma'am? So here, what does capacitor does? And we mostly talk about PPC, which is parallel plate capacitor. Right? Parallel plate capacitor. There are other types also which we will be discussing though. Majorly, we will be discussing this parallel plate capacitor. So what are these parallel plate capacitor? Parallel plate capacitors basically are those which are, by name itself is there. There are two parallel plates which are connected. Three-dimensionally when you are trying to see them, there are two parallel plates which are connected with some voltage. Right? Which are connected with some voltage. This is the actual view. So you can imagine like there are two parallel plates. There are two boxes here. Right? There are two parallel plates. Within them there is a medium, and these two are connected with the external source. Right, ma'am? So in this, external source means that battery can be EMF, or we can say it is EMF of a cell or a battery. EMF of a cell or battery is connected to this parallel plate capacitor. So what is it? Capacitor is a electric device which stores charges, right? And also when it is storing some charges, it stores some electric field energy between these parallel plates, right? So there is a positive charge which will be stored by this, negative charge which will be there on the surface of this, and there is going to be electric field between these parallel plates. So that is what capacitor is. It's an electric device which stores charges, or we can also say it stores electric field energy. Right, ma'am? So here, that is an introduction part. What is it? We have seen where we use. We have discussed how it works. Let us discuss how it works now. Let's say here, wherever a positive higher potential plate is connected to this, right, this will try to give, or slowly there is going to be charges that is going to be stored in it, and slowly capacitor, when t is equal to 0, it behaves as a short circuit. Right? It behaves as a short circuit, which means there is going to be totally charged, and slowly the charges are going to be stored on these parallel plate capacitor, and what is going to happen? Slowly this is getting stored some charges. When it is storing some charges, it is also storing some electric field energy. So here the higher potential plate usually stores positive and lower potential plate is usually going to be negative. Whichever is on higher potential side, usually it stores positive charges, and usually the other plate stores negative charge. And remember, it does not mean the net charge is going to be zero. Remember, whenever charges are there asked, the total charge is going to be only Q, right? So how is this Q, or how this works here? The amount of charge that is stored in capacitor is directly proportional to this electric potential difference, electric EMF of a cell, or electric potential difference that is given across the plates. Electric potential difference that is given across the plates. Right now, so here whatever the charge that is acquired by the capacitor is directly proportional to voltage, and the charge, when you are taking proportional to the equality, the constant that we call is capacitance of a capacitor, which is defined by C here. C is defined by Q by V. The amount of charge stored per unit potential. Capacitor is a device, and remember this C is basically called as capacitance of a capacitor. Capacitance of a capacitor. So capacitance of a capacitor is a device. The capacitor stores how much charge for a unit potential given. So here, what is the charge that it can store if a unit potential is given? So 1 voltage, 1 coulomb. So what is going to be unit for the capacitance here? Charge unit is coulomb. Charge unit is coulomb by unit for potential is volt. So coulomb is the symbol, volt, D is the symbol. So this unit we call it as 1 farad. Right? So 1 farad. So right now here, capacitance of the capacitor is defined as the amount of charge that is stored per unit potential developed or given across the parallel plate capacitor. Here net charge plus Q minus Q, net charge is not zero. What is the charge here? Q is the charge. One of the plate is storing positive charge, the other one stores negative charge. Clear with this now? So now think about it. So this, how much charge it can store? This is the fourth question, very important question. So people may think that it can store huge amount of charges, right? Whatever is, let's say I am giving 1000 volt to this parallel plate capacitor still work? No, right? There is a breakdown voltage. There is a breakdown voltage for every device. For every capacitor, there is a breakdown voltage. So breakdown voltage. So maximum amount, right? Whatever is the voltage given across these parallel plates should be less than or equal to breakdown voltage. So every capacitor device, they will mention us what is the breakdown voltage of that. So more than that, we cannot use this potential difference. Cannot be more than the breakdown voltage. What happens when it is greater than breakdown voltage? The charges may maximally stores and it might actually try to leak the charges. More heat will be developed. Sudden electric field, greater electric field is there. What is going to happen? More electric field or more electric field is there, with higher potential is going to be there, and breakdown voltage may occur of order of 10 power 6 volt per meter. Probably you would have learned that in electrostatics, whenever electric field is very high, what is going to happen? There is going to be lightning that is going to be formed. So, if a breakdown, if voltage given is greater than breakdown voltage, what is going to happen to the capacitor device? Either it will lose its functionality by trying to leak some charges suddenly by giving some electric field, high electric field is there means it is going to release like a lightning, right? And it might stop working as well. So that's the maximum charge it stores depends on the breakdown voltage of a particular capacitor, for which the values of this capacitors only they will give us, right? And different arrangements of parallel plate capacitor. So in these cases, right, first thing that you need to know is a capacitor is a device which stores electric field energy, right? And also where what is capacitance of a capacitor is defined as a charge stored per unit potential, and know that it is very important for engineering students and also those who are preparing for medical, who are preparing for NEET, also JEE and NEET students. For both, it is very important topic and it is going to be very interesting if you are learning slowly about this parallel plate capacitor. So now let us try to see further of these parallel plate capacitors and how it works, right? And usually the value of this capacitance of a capacitor is nearly 711 microfarads for the earth. We consider, probably you would have learned it, earth is a huge source of charges. Whenever we are saying that earth is having 711 microfarads, so remember that microfarads is a very high value, right? So usually capacitance of the capacitor are measured in millifarads, right? Millifarad, right? 10 power minus 3 farads, right? 10 power minus 3. Milli means 10 power minus 3 farads. Microfarads means 10 power minus 6 farads, right? Milli means 10 power minus 3, micro means 10 power minus 6, and nanofarad means 10 power minus 9 farads, right? 10 power minus 3 farads, 10 power minus 6 farads, or picofarads. Pico means 10 power minus 12 farads. Right, are you able to see this clearly? I hope you guys are able to see this clearly. So try to know capacitance of a capacitor values will be usually in terms of farads. Either it will be microfarads or nanofarads or millifarads. So these are the things very important, and try to know here at t is equal to 0, capacitor will behave as a short circuit for time t is equal to 5 times of R into C. We will discuss this in a steady state analysis of capacitor. So for time t is equal to 5 RC, capacitor almost reaches 98% of charge, which means then capacitor will behave as an open circuit. At steady state we call it, right? This is the steady state, right? This is the steady state. T is equal to 5 RC is basically going to be a, I'll try to keep this aside so that you can try to see the complete thing, right? So steady state, right? Steady state of a capacitor basically means maximum amount of charge is stored by the capacitor, and then capacitor at steady state will behave as open circuit. Clear this idea here now? So I want you guys to get this into your thoughts and get this into your mind and heart, that capacitance of the capacitor is defined with charge over unit potential, and in an open circuit, in like at t is equal to 0, it behaves as a short circuit where the entire charges will be passing through it. So when steady state is 5 times of RC, nearly 98% of charges will be stored. At this point, we call it as a steady state, where maximum amount of charge, if it is stored by a capacitor, then there is going to be what? Capacitor will not allow any current pass through this. Clear this idea here now? So this capacitor, right? Parallel plate capacitors and different arrangements of parallel plate capacitors, right? we'll be seeing that different arrangements of parallel plate capacitors and how does parallel plate capacitors work. So this parallel plate capacitor, right, this PPC, parallel plate capacitor, how is capacitance is defined as, and how this capacitance of a capacitor will change. Now I want you guys to think about this a little bit. How can we change capacitance of a capacitor for a parallel place? Right now, I want you to think about how can we change the same parallel plate capacitor for the parallel plate capacitor for the parallel plate capacitor. How can we change the capacitance of the capacitor? Can we increase how much charge it can store? Yes, we can do that with things. Now I want you guys to think whether it changes Q is equal to CV. Thus voltage and charge changes the capacitance of the parallel plate capacitor. I want you guys to think a little bit about it. So think about it. So here we have taken the C is independent of Q and V because C here is taken as constant. See here we have taken as what now? Constant. So I want you guys to know that if there is a constant, it does not depend on what now? It does not depend on what? It does not depend on the charge or the voltage that is given to it. Right now. So here whenever we are connecting this with a greater charge or greater potential is given, means greater charge will be there, but that does not change the value of the capacitance of the capacitor. So what does change? C is equal to Q by V. So here we have to see what values does it change the capacitance of the capacitor. So here we have already taken this mark, so I will be taking the same thing to explain about it. So here let's say this one is having plus Q or plus sigma. This is minus Q or minus sigma. What is sigma here? Charge density. Areal charge density, probably we would have discussed about it already. So sigma is what? Q by A. And what is minus sigma is negative charge density that the another plate is having, which is connected to lower potential. So here Q is equal to or V is equal to, what is the potential given here? He is giving us electric field between these parallel plates. So there is electric field between this parallel plates here. So there is a relation between this. If D is the distance between the two parallel plates, how we define electric potential as? Electric potential is defined as what? Electric field into distance between the two plates. We have seen that the relation between electric potential and electric field. So the relation between electric potential and electric field is what now? We have a relation which is directly proportional, right? Potential is directly proportional to what? Electric field and also distance between them. So E is equal to V by D because electric field, the unit is taken as, electric field is given as V by D, which is another unit for electric field, which is volt per meter. E is by this formula. And the potential is defined as what? E into D. We take it as minus here, but we are neglecting the sign convention. So here, what is Q by V here is what? Electric field into distance. What is electric field between two parallel plate capacitors? I want you to think about it. Whenever positive charge is there and negative charge is there, so electric field due to positive charge and due to one plate is given as sigma by 2 epsilon naught. This is electric field due to plus, and electric field due to negative is towards the negative plate. So electric field minus is again given by same sigma by 2 epsilon naught. So what is going to happen to the net electric field? What is going to be happen to the net electric field? So net electric field is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So that will be happening in this direction, which is sigma by 2 epsilon, sigma by 2 epsilon naught. So LCM, if you are taking sigma plus sigma, that will become 2 sigma by 2 epsilon naught. Denominators are same, numerators can be added. So net electric field will be what now? Sigma by epsilon naught. So net electric field between two parallel plate capacitors is taken by sigma by epsilon naught. So here C is equal to Q by V, Q is E by D, where E is given as sigma by epsilon naught into D. And we can also write sigma as Q by A, epsilon naught will be going in the numerator. Right, sigma is Q by A into D. So this Q gets cancelled here. So what is capacitance of the capacitor is defined by epsilon naught A by D. So capacitance of the capacitor does not depend on charge or potential that is given across the parallel plate capacitors. Right, and here what should be the capacitance of the capacitor depends on the medium, right? Depends on the dielectric medium, right? Dielectric medium present, dielectric medium present between the parallel plate capacitor PPC. Parallel plate capacitor, between them there is a dielectric medium, and that is what is giving us the capacitance depends on this dielectric medium, and also it depends on the area of cross section between the plates. Area of cross section between PPC, right? Section between PPC. Parallel plate capacitor only we are discussing about. Capacitance of the capacitor depends on these. And D here, what is D here? Distance between the two parallel plates. Distance between two parallel plates, or two parallel plates is fine. Two parallel plates. E is going to change the value of this capacitance of the capacitor. So which means if I am giving the same source, right? Giving the same source V. Now I can increase the charge that the capacitance can store by either increasing the area, right? We can increase the area, or we can use there as a medium which is having a high dielectric strength, so that charges cannot be leaked, so that maximum charges can be stored in the capacitor, between the capacitor, on the parallel plate capacitors. So and maximum electric field also will be there. So distance between the parallel plates should be decreased. So these are the things which can increase the capacitance of the capacitor. If capacitance of the capacitor is increasing, charge stored on it, Q is equal to what? C into V. If V is constant, charge also going to be, right? Charge also going to be increased. So when capacitance, right, the upper arrow usually I represent for increasing, lower down arrow I represent it for decreasing, right? I am trying to write that as well. Upper arrow represents what? Increasing. Lower arrow or down arrow represents what? Decreasing. Right now? So these are the things. This is how a parallel plate capacitor works, and how these charges are stored, and what is the maximum charge it can store depends on the breakdown voltage of the parallel plate capacitor. Right? So you have this in your mind and your hearts, so that you can try to understand this in a better way. So remember, capacitance of the capacitor does not depend on what now? Charge, or the capacitance of the capacitor does not depend on the charge or the potential drop given to the parallel plate capacitor. Understood now? So let us go forward, right, and see what are the different arrangements of the parallel plate capacitor. Now that we have learned that what is capacitance of the capacitor depends on dielectric medium, right? It depends on the dielectric medium, and also parallel area between the area of cross section of the parallel plate capacitors, and also it depends on what distance between the parallel plate capacitors, right? So these are the things, right, which capacitor is depending on. So before going further, so I wanted to solve a few problems on PPC. So what is parallel plate capacitor? So they can ask you, they give some voltage, right? Now they give some voltage 100 volts, and they give some voltage of 100 volt, and they will say that capacitance of the capacitor is 10 microfarads, right? So 10 microfarads. What are the things they can ask you here, right? So they say that initially the switch is there at t is equal to 0. At t is equal to 0, switch is switched on, and then the maximum charge that the parallel plate capacitor can store, right? What is the maximum charge that the parallel plate capacitor can store? Q maxima. Here applied voltage is V here, so consider that V should be less than the breakdown voltage. If nothing is mentioned, we have to assume this automatically. So Q max is equal to C into V given to it. So Q is C is what? 10 microfarad into volt here is given as what? 100 volt. So what should be this one? 10 into 10 power minus 6 farad into volt will be coulomb into 10 square. So that will be what? 10 square into 10 power 1, 10 power 3 into 10 power minus 6, that will become 10 power minus 3 coulomb. Or in other words, we can say 1 into 10 power minus 3, right? 6 minus 3 minus 6 is minus 3, so that will be 1 millicoulomb. So in the same question, they can say how much should be, and if 1 millicoulomb is taken, how much should be the value of dielectric constant, so that I can change the medium present between them, so that the charge is increased by 100 times. Now, increased by 100 times, what is the charge? Or what is the dielectric constant of the medium that we have to introduce? Dielectric constant of medium introduced. Right, this is second question. First question they are asking about maximum charge stored. Second question, what is the dielectric constant medium introduced so that charge increases by 10 times or 100 times? 10 times is one question A, or charge increases now. Charge increases 10 times. 10 times it increases, or charge increases by 100 times. Charge increases by 10 times. Charge increases by 10 times, or say 20 times, or say 100 times, or 70 times. Let's take 50 times. Right? So what is the amount of charge? Maximum charge is given. So now tell me here, how this can be like maximum charge can stored be increased here, because here source is constant, right? What is dielectric medium introduced so that charge increases by 10 times, 20 times, or 50 times? So here what can be increased? Capacitance can be increased. So what can be? Charge should be what? Q maxima, it should be 10 times, this is C naught, let us write 10 times of C naught into V, which means capacitance in the medium should be 10 times of C naught. Capacitance in the medium should be written in terms of what now? Dielectric constant time. So which I think we have to discuss. Whenever medium is changed, Cm will become epsilon m A by D here. 10 times of C naught is going to be epsilon naught A by D. What is epsilon m here? 10 times of E naught. So there is a concept between what is relative permittivity. Probably I think we have learned it. Relative permittivity is permittivity of a medium by permittivity of a free space. So which is also taken as dielectric constant or relative permittivity. It is a measure of how much electric field lines cannot be allowed by that medium. So dielectric constant is defined, or EM we can write as what? ER into epsilon naught. All these things probably earlier when we are discussing about medium, between whenever medium is changing, dielectric force between the two charges will change, dielectric strength or electric field also will change. So EM we can write as ER into epsilon naught. So for 10 times, what should be ER value? 10. For 20 times, what should be ER value? 20. And for 50 times, what should be ER value? 50. Because only that value changes the charge that can store maxima. Right now, because medium is different, instead of capacitance in a medium, capacitance free space, we have the capacitance in the medium. So we need to know that the relation between capacitance in the medium and capacitance in the medium and capacitance free space you need to get by this relation. Probably C naught is what? Epsilon naught A by D. Cm is what? Epsilon m A by D. When epsilon m is taken as what? ER into epsilon naught. So Cm is taken as ER into epsilon naught A by D. So C in the medium is equal to ER times of C naught. Sir, is there any other way? So what if the same question they are asking, this 10 times, 20 times, 50 times, instead of changing dielectric constant, can we change the distance? Yes, we can also change the distance, right? So because here, when distance is changed, we can write it CD here. New distance, epsilon naught A by D1. So try to know here, if this value CD1 should become 10 C naught, CD1 should become 10 into C naught, where C naught is what? 10 times of epsilon naught A by D. CD1 is what? Epsilon naught A by D1. Epsilon naught A get cancelled. So then what is going to be D1 here? D by 10. So if the distance is decreased by 10 times, or distance is decreased by 20 times, or distance is decreased by 50 times, then the charge on it can be, the charge on the capacitor stored can be increasing. So this is very good question actually, which includes with a very basic idea of how charges can be stored between this parallel plate capacitors. Right now, see different connections of parallel plate capacitors, right? Different arrangements of PPC, different arrangement of PPC. This is most interesting one. So I think you should be knowing that whenever different arrangements are there, we discuss about what? Series and parallel connection, right? So what is constant in series and what is constant in parallel, and what divides or what adds up in series and parallel connection is very much thing that you need to know here. Right? So here, whenever two parallel plate capacitors are connected in series, so like this, if you are connecting, and you are connecting this with the source voltage of V here. Parallel means you are connecting one to the other one with a constant potential drop between these. Right now, between this. So here, parallel in the same array, this is AB here. We know how to write this. This is AB here. This is AB here. Same potential drop will be there between these two parallel plate capacitors. whenever it is A here, this is B here, wire connected to the same wire will have same potential. Wire connected will always have the same potential throughout. And if you are looking at here, you are connecting this with A, this with B here, this is also going to be B, this is also going to be B, A, so this is going to be what? C here. So there is different potential difference between this is C1, this is C2, and this is C1 here, this is C2 here. So both together we will try to see here, in parallel connection what is constant? AB, this has the same potential drop, this has the same potential drop. So what is same here? Same potential difference or potential drop across the capacitor will remain same. Same potential drop will be there. So in this, what is going to remain same here? Same current will be there. So same charge will be flowing entire circuit. So there is going to be plus charge. This is going to be negative charge because this is connected to negative side. This is positive terminal is connected to the higher potential. This is going to be negative terminal. So same charge will be flowing in the circuit. The same charge is flowing in the circuit throughout. So same charges will be stored in series connection. So same potential drop here, but here what is same here? Same charge flow or flowing. Same charge is flowing throughout. So this same charge is flowing means what we can say here? Charge value is current. Basically, current is same in series. Potential drop divides or answer. So potential drop, I will try to take potential drop as PD here. Right, potential drop as PD here. I have already taken that. So PD divides or answer. Divides or adds up. Right now, so whereas here same charge will not be there. This is going to have a Q1 here, this is going to have a Q2 here. So in this, what is potential drop divides or adds up here? So we always know equivalent capacitance means replacing these two with one single C equivalent which is across AB. It can be either series, C equivalent parallel here. Here I am replacing these two with C equivalent in series. I am connecting with the same potential drop here. So what is dividing here? So here total voltage given is V here. Whatever is the potential V here should be equal to VAB is equal to VA minus VB. We can write it as VA minus VC plus VC minus VB. So what is VA minus VC? We can write as potential drop across AC plus VCB is nothing but potential difference across CB. How is VAC is taken as now? How is VAC is taken as now? VAC is Q by C1. So VAB is on left hand side we take equivalent C equivalent series is equal to Q. The same charge should be stored in this. So Q by C1 plus Q by C2. So charges will be cancelled here. So what is the relation that we get here? Now this relation is very important. 1 by C equivalent in series is equal to 1 by C1 plus 1 by C2. Whereas in parallel connection, what is dividing here? Charges are dividing, right? Q is dividing or adding up. Q is total charge is dividing and the total charge is adding up. So we try to take whatever is dividing and try to find out the C equivalent. So we are connecting this with the external source here with of AB here. So Q total is equal to Q1 plus Q2. Here total charge is going to be there, the same total charge will be there here. So whatever is the total charge here is going to be divided with Q1 and Q2. Q total is going to be what? C equivalent parallel into V. On left hand side we take equivalent, on right hand side we take C1V plus C2 into V. So what is going to be V here cancels. C equivalent in parallel will become what now? C1 plus C2. So remember this is similar to what? series resistors when it is connected in series, R equivalent is R1 plus R2, but that happens in where? Parallel connection for capacitor. So you can remember it this way that it is exactly opposite to what? Resistors that we have seen, right? The same thing here, whenever they are connected in series, whenever they are connected in series, right? So whenever they are connected in series, we get 1 by C equivalent is equal to what? 1 by C1 plus 1 by C2. So now let us discuss in detail about this, right? Series connection. Right, in detail about this series connection, let us see, and then we will come to parallel connection. So C equivalent we have derived it. I will be utilizing this result later. But now I want you guys to think about it. What is going to be the potential drop? Here charges on both the parallel plate capacitors in series connection remain same. Right? What is going to be the potential drop? Right now, what is going to be the here? This is how we define the C equivalent in series. Now I want you guys to think about how we try to talk about parallel connection, series connection, how voltage is divided. So remember here, potential drop across AC is going to be what? Q by C1. Potential drop across CB is given as what? Q by C. So what is going to be ratio of VAC plus VCB here? Ratio of VAC by VCB is going to be what now? Q by C1 by Q by C2. Q get cancelled. So what is that we get here now? VAC by VCB we get it as C2 by C1. C2 by C1. So which means potential drop across AC depends on the capacitance of the capacitor of second one. This may not be the true for 3 capacitors. For 3 capacitors we have to take Q by C1, we have to take C equivalent and then try to find it. So here, how do we write Q here in terms of C equivalent? So what is C equivalent in series connection? If you are taking LCM here, C1 into C2, this is going to be into C1. Into C1, this is into C2. So what is going to be C equivalent in this one? C equivalent in series is going to be C1 C2 by C1 plus C2. Correct? C1 C2 will be denominator. C equivalent is C1 C2 divided by C1 plus C2. So here, how can we write potential drop across AC here now? Potential drop across AC we can write as Q by C1, where Q is nothing but C equivalent in series into voltage by C1. Similarly, potential drop across CB is C equivalent in series in voltage by C2. So what is C equivalent here? C1 C2 by C1 plus C2. So VAC we can also write C1 C2 by C1 into C1 plus C2 into voltage. So this C1 get cancelled. And what is VCB here? C1 C2 by C2 into C1 plus C2 into voltage. C2 get cancelled. And what is that we get here now? Potential drop across AC depends on what? C2. VAC depends on what? C2. VCB depends on what? C1. So VAC we can write in terms of total voltage C2 into V by C1 plus C2. And what about VCB here? C1 into voltage by C1 plus C2. Clear this idea here now? So potential drop across AC and CB, right? Potential drop across AC and CB is directly proportional to other capacitance of the capacitor. VAC is equal to C2V by C1 plus C2. VCB is going to be C1 into V by C1 plus C2. So it is very important to know or understand that how this potential will be divided only when 2 capacitors are there. When 3 capacitors are there, we have to take again the same concept. VAC is going to be Q by C1, CD is going to be Q by C2, BCB is going to be Q by C3, Q we have to take C equivalent. C equivalent when 3 are placed, 1 by C equivalent is equal to 1 by C1, 1 by C2 plus 1 by C3. We have to write it and try to take these voltage values accordingly. But this result we can directly use when two parallel plate capacitors are given. So potential drop will be directly proportional to what mark? Other capacitance when two of them are connected. So when the same thing here. So whatever is the total voltage here, right now, whatever is the total voltage here, V is equal to, right? V is equal to VAC plus VCB. From this also we can try to find out VAC is equal to C2 times of VCB, C2 C1 by C2 times of VCB. From this also we can try to find the relation here, right now. So whenever three capacitors are connected, then 1 by C equivalent in series, 3 are connected. 3 different capacitors are connected. Then 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So taking LCM here, C3 should be multiplied with C2 C1. This is C2 C1. This is C1 C3. This is also C1 C3. C1 is multiplied with C2 C3. This is multiplied with C2 C3. So what is going to be C equivalent C1 C2 C3? C equivalent in series is going to be what? C1 C2 C3 by C1 C2 plus C2 C3 plus C3 C1. So this result, if there are 4 capacitors, what changes will be there now? You have to write it directly. C1 C2 C3 C4 divided by C1 C2 C3 plus C2 C3 C4 plus C3 C4 C1 plus C4 C1 C2. All the combinations, all the 3 possible combinations we must take and try to write C equivalent. If 4 or 5 are connected also, you should be able to write this direct formula. But potential drop, as in series connection, charges are same. You have to take Q by C1, Q by C2, Q by C3, Q by C4 or Q by C5. If 5 capacitors are connected, Q we can take as C equivalent. C equivalent into V. C equivalent in this case is what now? C1 C2 C3 by C1 C2 plus C2 C3 plus C3 C1. C equivalent place we will get this result and only C1 will be cancelled. So C equivalent in series. So VAC is going to be C2 C3 by C1 C2 plus C2 C3 plus C3 C1 into voltage. So like that you should be writing potential drop across each parallel plate capacitor. Clear this one? Right, so you should be getting these things, right? So now we will try to see further for parallel connection how these things will be coming. We know it is same potential difference, charges will be divided. Both are connected with same potential drop. AB here, same potential drop. AB, same potential drop. AB, this is C1, this is C2 here. Charges stored is going to be Q1. Charges stored on this is going to be Q2. This is going to have a total charge. So what is going to be C equivalent here? Both these are combined and taken as V here. What is divided in this? Charges will be divided. So here total charge we are taking Q1 plus Q2. So what is it we get here now? Q1 plus Q2. Q total is going to be C equivalent parallel into V here is VAB. C1 into V plus C2 into V. So here, so C equivalent into V is equal to C1 into V plus C2 into V. Voltage remains same. So C equivalent in parallel is going to be C1 plus C2. If there are 3, then C1 plus C2 plus C3. If there are 4, C1 plus C2 plus C3 plus C4. So try to know here what is different in this. Q1 is C1 into V. Q2 here is C2 into V. So what is going to be ratio of the charges stored here when it is in parallel connection? Directly proportional to the capacitance of the capacitor. So Q1 by Q2 is going to be what? C1 by C2. So directly proportional to this. If there are three capacitors, Q1 is 2. There are three capacitors. Q1 is 2, Q2 is 2, Q3 is going to be what? C1 is 2, C2 is 2, C3. And how do we write this ratio here? Remember, Q1 by C1 is equal to Q2 by C2 is equal to Q2 by C1, which is nothing but potential drop across AB. VAB is nothing but Q1 by C1 or Q2 by C2 or Q3 by C2. Sometimes they will give two charges and they will ask us to find out the third charge. This is Q3 here now. If they are asking for third charge, you can try to take these ratios and try to find out. So whenever three ratios are there, try to remember Q1 by C1 is equal to Q2 by C2 is equal to Q3 by C3. That is how we take when three ratios are there here. If four ratios are there, also same thing. Q1 by C1, Q2 by C2, Q3 by C3 is equal to Q4 by C4. And whenever there are equal capacitors in parallel connection, then C equivalent parallel is going to be what? C plus C. If there are two capacitors, that will be 2C. C equivalent, if there are three capacitors, C plus C, which is 3C. Remember, when there are n capacitors, n equal capacitors are there. If n equal capacitors are there, then C equivalent parallel is going to be what now? N times of C. N gives us the number of capacitance and C gives us the capacitance of each capacitor, which is equal we are taking in this. So that is how we get equal capacitors in parallel. Similarly here, if equal capacitors are taken in series now, equal capacitors in series connection. So equal capacitors in series connection is what? C equivalent in series is equal to, right, C1, C2. If two capacitors are there, 1 by C equivalent is equal to 1 by C plus 1 by C here. So C equivalent will be 2C by 2. If two capacitors are there, C by 2. If three capacitors are there, C equivalent in series is C by 3. If there are n equal capacitors, it is going to be what now? Now 2 by C is equal to 1 by C equivalent we get. So if there are n equal series capacitors, if there are n equal capacitors placed in series, then we can take C equivalent in series is going to be what now? C by n. Clear this idea here now. So you have to know these kind of things. It's very important to learn this, right? And the different types of arrangements of parallel plate capacitors and problems based on parallel plate capacitors you have to know in these, right now. So more about this, we will try to solve some applications, at least one or two applications based on series and parallel connection arrangements, right? So you will see this interesting question, right? We will see this question which talks about what is C equivalent across AB, what is total charge, right? What is the total charge on these capacitors, what is potential drop, and our charge stored across each capacitor. So how do we solve these kind of problems? We will try to see here. So take the C equivalent, C value, all of these have same capacitance C, and C. Let's say that the C value we will try to take. So Q is equal to C equivalent into V. So what is going to be C equivalent across AB mark? C are connected in series, so that will be C by 3. C and C are connected in what? Parallel. So these two is going to be what? 2C. This one, and this one, all the three are connected in series, so that will be C by 3. So all these three together, like we can try to shift this, branching the capacitor, like we can try to shift the capacitor on this side, that is going to be the same connection that we will have. Right? Now, what is going to be C equivalent across AB? Now this will be like C by 3 and 2C are connected in series. C by 3 and 2C are connected in series, connected with a 100 volt here. So try to draw this C equivalent in series, C1 C2 by C1 plus C2. So C equivalent across AB will be what? C equivalent across AB is going to be C1 C2. It will be 2C into C by 3 divided by 2C plus C1 plus C2. C1 C2 by C1 plus C2. So 2C square by 3. So one of these C's will be cancelled. So you get an LCM here, 1 into 3 into 3 into 1 into 1. So 2C by 3 divided by 3 into 2, 5 plus 1. 3 into 2, 6 plus 1. That will be 7 by 3 here. 3 get cancelled. So what is going to be C equivalent across AB here ma? 2C by 7. So C equivalent AB is going to be what ma? 2C by 7. So what is C equivalent? We found it as 2C by 7. Let us write 2C by 7. Now what is the second thing they are asking? What is the total charge? Total charge means 1 C equivalent AB is going to be there. So Q total is going to be C equivalent AB into voltage across AB. C equivalent AB is 2C by 7. Voltage is how much? So 200 by 7C is going to be the total charge of this combination of this capacitor. Now what is potential drop? What is potential drop across the potential drop of charge stored across each capacitor? Now we know that series same charge will be there. So we will have a positive, we have negative, we have positive, we have negative. So here 200 by 7 coulomb will be there on this. Same 200 by 7 coulomb will be there. This is having positive, this is having negative. Right? So here same charge will be there, 200 by 7. Same charge will be there, 200 by 7C. 200 by 7C. Here it's going to be 200 by 7C, but in parallel connection charges will be equally divided because we have same capacitor. So that will be 100C by 7. This is going to be 100C by 7. Now what is the potential drop across each capacitance of a capacitor? Potential drop across AC, how do we write it ma? VAC. VAC is going to be what ma? Q by C. So that will be 200 by 7 voltage. Q by C, VAC is Q by C. So 200 by 7 C by C, that will be 200 by 7. Similarly VCD also is 200 by 7. Similarly here it is going to be 200 by 7. Whereas here 100 by 7. So this is VAC. VCD is also going to be 200 by 7. C equivalent is going to be 2C here. So VCB. VCB is going to be Q by C. So 100 by 7 voltage. Q we are taking this, by C we are trying to take this. Similarly Q by C, Q is this is charge on EB, this is charge on AC, this is charge on CD. So here charge on D of these capacitors will be remaining same. VCB is going to be 100 by 7. And if you are trying to add all these up, 200 by 7 VAC and VCB is 200 by 7, 400 by 7, 500, 600 by 7 plus 100 by 7, 700 by 7, which is going to be what? 100 volt. We have to cross check this so that you are very sure about the answer that you made. So these are very interesting problems that you can solve in series and parallel connection. These are the possible questions they can ask based on series and parallel connection. Right now, thank you guys. More about this we'll try to see it in next class.